Hello, we will now talk about Chapter 8, Section 3, which deals with two proportion z intervals, otherwise known as a two sample z interval for the difference in proportions. And so now we're going to have two populations, and we're going to make an interval with the difference in the proportions of those populations. Whereas in Section 2, we just had one population and one proportion and made an interval in regards to that. So let's look at this context here. So this says Finn wishes to estimate the difference in the proportion of boys at his school that play a sport and the proportion of girls at his school that play a sport. He takes an SRS of 150 of the boys and finds that 90 of them play the sport. He takes an SRS of 160 of the girls and finds that 80 of them play a sport. Create a 95% confidence interval for the difference in proportions of the boys and girls that play sports for the entire population, school, state, the standard error, and the margin of error. So we're asked to make a confidence interval. Now, when you're dealing with a difference in two proportions, all right, first of all, when you're making a confidence interval, it is expected that you are going to go through the TAME acronym. Whenever you make an interval, you have to do these four things. You have to state the type of inference. You have to check the assumptions, otherwise known as the conditions, and you have to verify them. In other words, you have to say whether or not you think they're true in this situation. You have to do the mechanics, which means to create the interval, and then you have to state your ending in context, draw your conclusion in context. You have to do those things. And with your assumptions, now with your assumptions with a one sample interval, you had to send. You had to, is it an SRS or is it random? All right, do you have independence? That means is your sample size less than or equal to 10% of your population size? And you have to have normality. Okay, and so that spells out sin. Okay, so that's with the one sample. With the two sample, it's not just sin, it is I sin. Okay, we have another application of the word independence. Okay, they have to be independent random samples. You have to state that. In other words, the samples could not have been influencing each other in any sort of way. And you can't have any sort of pairing going on, which we'll talk about later in the year. And this is a different kind of independence where your population size needs to be big enough. Okay, and then your normality, n times p and n times 1 minus p, have to be greater than or equal to 10, but it's p hat, since we don't know what p is. That'd be greater than or equal to 10, but it's got to be true for both populations, n times p and n times 1 minus p for both populations, in this case, for the boys and for the girls. All right, and so that's what we're going to do. We're going to do the little TAME acronym to create our interval, and it takes some work, but it's an easy way to get a lot of points. And so first of all, the type of inference when you're creating, you have two proportions, just the two proportion z interval. Sometimes you may see it written as a two sample, as I mentioned earlier, two sample z interval for the difference in proportions. Difference in proportions. And so like in a multiple choice situation, you may see it written, you may see it written that way, but the quickest way to write it is just to say that. And there you go. That is the type of inference. And so then we must verify our conditions, which is I sin. So we would say this, all right, first of all, is it an SRS or is it random? All right, you would say it says SRSs were taken, so independent random conditions met. You must say independent random conditions met. In other words, there's no reason to believe the samples were influencing each other in any way. But that is a common thing. If you leave out the word independent there before random, you'll get partially correct for your assumptions at best. So make sure on the two sample things that they're independent. You say independent random. All right, so then the other aspect to the meaning of the word independence, our population sizes must be at least 10 times our sample sizes, in essence, so that in essence, our sample sizes are less than or equal to 10% of our population. So since our sample size for boys was 150, there must be at least 1,500 boys, and the sample size for girls was 160, it's got to be at least 1,600 girls for our n's to be less than or equal to 0.1 times our big N's. And so we don't know this for sure. And so that's what we would, say there. And then lastly, for our conditions, which is kind of the most involved part of it, our n times our p's and n times 1 minus p's for both the boys and for the girls have to be greater than 10. Well, what is n times p? our p hat for the boys here is 90 over 150. Okay, so then these should be hats. Sorry, these should all have hats because we don't know what p is. So we have to use the hats. And so it's 90. So this would be 150 times 90 over 150, which is just 90. In other words, your number of successes for the boys, so to speak. Okay, and so this is just going to be 150, times 60 over 150, which would be 1 minus 90 over 150. So it's in essence, these things are just your number of successes and failures for the boys. That's your number of successes, number of failures for the girls. You don't have to show the letters. You just have to show these numbers here. That's what they're looking for. And then clearly state they're greater than or equal to 10. And you'd say, thus normality's met. Okay, so that's important that you say whether or not you think the conditions met. And so there's your ISIN. So every time you do this two sample thing, ISIN. Now let's do the mechanics. Okay, so here's our mechanics, and I've got a little shortcut, with your calculator. I'm going to show you. Say, okay, first of all, let's talk about that formula there. So for any confidence interval on the first page of the formula sheet has this formula: statistic plus or minus critical value times the standard error of the statistic. Well, here the statistic is actually the difference in our statistic, which is 0.6 minus 0.5. It's the difference in our p hats. That is our statistic. Our critical value is our z star. Let me remind you where to find that. When you go to table B, it'll tell you your z star by going to the bottom of the table. It was told to us in the problem to create a 95% confidence interval. The z star is the number right above it. There you go, 95%. And that's certainly the quickest way to find your z star. And then there's your standard error. There's your standard error. And so the standard error, the way you find the formula for that is you go to page 2 of your formula sheet, and for proportions here, and so there is the difference for proportions. It's the square root of, and then p hat times 1 minus p hat over n for both the boys and for the girls. Okay, and so there you go. And so this right here, there's your standard error. It asks up in the problem, it asks what's the standard error. There it is. And then the margin of error is just critical value times the standard error. So it is just 1.96 times that, which is 0.1102. And so that's, in essence, your margin of error. The margin of error is how far the interval goes to the left and right from your point estimate, which is the middle, which is 0.1 here, the true difference. And so I said 0.1 plus that to get that, and 0.1 minus that to get that, and there's my interval. So that's how you do that. Now, you say, how much work do I have to show? The answer is you only have to show the interval. But there's kind of a give and take there. If you show the formula, if you make a mistake and you get the wrong interval, you can still get partial or possibly even all credit. But the problem is if you get the right interval, but if you do something wrong here, you can have points counted off. And obviously this takes more time. So let me show you how to use your calculator to get it. I in general, like to conserve time, I would just use my calculator to get the interval and write that down. Then when I get to the end of the test, I get everything else done. I could come back and write out the formula if I have extra time. So that's kind of what I advise you to do. So let me show you how to use your calculator to do this. And so the function for your calculator to create a 2 proportion z interval, it's in the, so I hit the stat button, I hit stat and go to test, and I scroll down to option B. So in this chapter, there's 2 calculator functions we've got to use, A and B here. So it's like the 12th one down B. So I hit enter. And so the first thing I enter is, so the X for the boys and the N for the boys. So X is the number of successes for the boys, and it said 90 out of 150. So I go 90, and my sample size for the boys is 150. And then for the girls, it's at 80 out of 160. So I hit 80 out of 160. That's what I was given in the problem. Now, these have to be integers, okay? The other way they could give you this problem, they could give you the p hat. They could give you 0.6 or 60%, and then the sample size. And you'd have to find X by saying 0.6 times 150 is 90, okay? And they could give you that the girls was 50% played sports, and the sample size is 160. So you'd have to say 0.5 times 160 to get that. These have to be integers. Your X's, or you'll get an error message. My confidence level is 95%, so I go 0.95. I hit enter on that, and there's the interval right there. And so that's all you have to write down for your mechanics, and you'll get full credit. And then lastly, whenever you make an interval, you have to interpret the interval in the context of the problem. And this is how you do it. You're always just going to say, I'm 95% confident, or whatever the confidence level is given in the problem, that that interval captures the true parameter, which in this case is a difference in the parameter. And so this is how we would say that. I'm 95% confident that this interval captures the true difference, is what we would say. Okay. Our sample difference is 0.6 minus 0.5, which is 0.1. But those are estimates of the true values. So we are 95% confident this interval captures the true difference in, and then say what the proportions are. The proportions of all the boys and girls at the school that play sports. And there you go. That's how you make a confidence interval. Okay, so then a couple other things. Number two, it says, does this confidence interval give us significant evidence that the proportion of boys and girls that play sports are different? All right, the key thing in regards, one of the big things in regards to this interval is, does it give us evidence that there's really a difference? And the thing about it is the big deal there is 0 in the interval. And 0 is in the interval. And what 0 represents no difference at all. So, and these are the plausible values for the true difference. So if 0 is in the interval, it's a plausible value. So there's plausibly no difference. If 0 was outside the interval, then that means that there appears to be a difference between the two population proportions. And so this is what we would say there. 0 is inside the interval. So it is a plausible value for the true difference. So there's plausibly no difference in the population proportions. So there you go. So anytime you do these two sample things, that's always going to be a big deal. And it's frequently going to be asked as to whether or not 0 is in the interval, because 0 represents in essence no difference. And in regards to the AP exam and in regards to tests, it's a virtual certainty that this, or at least part of this, is going to be in the AP exam. And frequently they'll ask you about part of it. They'll ask you about the assumptions. They'll ask you to verify the assumption. So you have to ISIN, or they'll ask you to create the interval, or they'll ask you to interpret the interval. Okay. So right there. So anyway, so there you go. So that's how you do that. So number 3, it says create a 99% confidence interval for the difference in the population proportions. Why is this interval larger than the 95%? Well, and I did that here. The only difference in a 99% interval, if everything else is the same, is the Z star. So there's our point estimate plus or minus Z star times our standard error. And the Z star for 99% is going to be bigger. The bigger and so you just go to 99% on the table and look at it above there. You'll notice the higher your percentage, the bigger your Z star. Okay. And so the bigger your interval is going to be, the wider your interval is going to be, because you're going to be more confident that it actually captures the true difference. It actually captures the true value. So the wider we make this interval, the more confident we're going to be. The skinnier we make this interval, the less confident we're going to be it actually captures the true value. And so in this case, the higher confidence level has a larger Z-star critical value. A wider interval means you are more confident that it captures the true difference. Now, I want to quickly, this is a bit of an aside, show you how to find Z-star using your calculator. This is certainly a good way to do it using a table. But let's say for 99%, and I did 95% on the last video. So let's do, for a 99% confidence interval, it in essence means that 99% of your sampling distribution, in a way, is taken up by the interval. Well, if 99% is in the interval, that means 1% is on the outside. In other words, 0.5% on the outside. This is 0.5%, and this is 0.5%. And the critical value is right there. And so we're going to use inverse norm with the standard normal curve. This is the standard normal curve, mean of 0, standard deviation of 1. That is the curve of Z-scores, and it'll tell us the Z-star. And so we'll do inverse norm. And so we'll do the percent that is to the left of our value, which is 99.5%, or 0.995. Mean of 0, standard deviation of 1. And that'll tell us the critical value. So in other words, to find a critical value, you just take your percent and you add on one of the tails, in essence. So let's do inverse norm. You go second vars, which is distribution, inverse norm, 0.995 mean of 0, standard deviation of 1. And there we are, 2.576 approximately. That's if you want to get a more exact value. So if we wanted 95%, like we did before, so 95, if we change this, well, I'm not going to do it twice. So I don't want the video to be too long, but anyway, so there you go. All right, so here, and so I've got another problem as well. This one has something else happen that you need to be aware of, specifically in regards to randomness. So this one says a doctor wishes to see if a new pain reliever works better for patients with back pain than the drug he currently uses. He has 84 patients with back pain that are available for the study. He randomly assigns 42 of them to the new drug. He did not randomly select them. He randomly assigned them. That's a different thing. These 84 patients, he did not randomly select from a larger population. So that's going to be an issue. But he did randomly assign them to take the new drug, and the other 42 took the old drug. In the new drug group, 28 of the 42 reported significant improvement of their back pain. And in the old drug group, 22 of the 42 reported significant improvement in their back pain. Create a 95% confidence interval for the difference in the proportions of patients like these that will have a significant improvement in their back pain after taking the new drug, and the proportion of patients like these will have significant improvement in their back pain after taking the old drug. We want to see the difference in the new and old drug as far as the proportions that have significant improvement. The big difference in this problem and the one on the other side is this, is they were randomly assigned. They were not randomly selected. So that's going to change our sinning a little bit, our I-sin, it changes that a little bit. So let's create the interval here. So the first thing is state what we're doing. We have to do the TAME acronym, the type of inference, the assumptions, mechanics, ending. You got to do those 4 things. Okay. So the type of inference, same thing, 2 proportion Z interval. Then, all right, in regards to your I-sin, they were randomly assigned. They were not randomly selected. Don't say they were randomly assigned. Don't say it was an SRS because they were not randomly selected. They were randomly assigned. So this is the way we're going to word this. It says they were randomly assigned. So the independent random condition is met for patients like these. The only patients we can generalize about are for patients that we have reason to believe are patients like these because they were not randomly selected. If they were randomly selected from a larger population, we could infer or generalize about that whole population. And so this is the way we're going to take care of that. And, and typically, in medical experiments, the reason that they can't, randomly select is it sort of can be unethical to try to force medical experiments on people. So you have to take volunteers. So now, because we didn't randomly select, we don't have to check the other independence condition. Our population size, our sample size being less than 10% of our population size. We don't have to check that because we aren't doing sampling. In essence, our larger population doesn't have really a limit to it. So if you did check it, it wouldn't be wrong. Okay. So you might want to just go ahead and check it every time, or go ahead and say that our sample size, there needs to be at least 840 patients like these, I guess you would say. Anyway, so you don't have to check that one when you don't have random selection. Okay. And then lastly, the other condition is still the same. Our N times P and N times 1 minus P for both the new drug group and the old drug group have to be greater than 10, and they are. You have, 28 out of 42, so that's 28 successes. And then if there's, 42 minus that is 14, it means you had 14 failures. And then the other group, you had 22 successes and 20 failures. They're all 4 of them had to be bigger than 10, and they are. And so you'd say thus normality is met. And so that's how you do that. And so that's the way you need to word that. Okay. Now, and then, so your mechanics. So there's your, now, I didn't show, this is all you had to show for your mechanics. So for mechanics, let's do that again. What you can do is you can go stat and then go to tests and then go down to option B and then option B. And so you would say, okay, so the first one's 28 out of 42. Once again, 28 successes out of 42. If they gave you the proportion, so in other words, if they gave you 0.6 repeating, which is what that fraction is, you'd have to multiply it by n to get that. And so then we got 22 out of 42, 22 out of 42, like that, right? Yeah. And so our confidence levels were 95% once again. So we do that. And so that's it. There's our interval. And so that's all you have to write down. And I didn't show the formula, and You could be asked to show the formula, you know, in another problem, or what happens a lot of times is they'll put this formula in a multiple choice situation. And so you need to be able to pick it out like that. So make sure you understand this, but when you're doing a problem, you can just write it like that. And then your ending is going to be this: I'm 95% confident this interval captures the true difference, but you have to stay it in context. I'm 95% confident that that interval captures the true difference in the proportions of patients like these. It's important. Patients like these that report a significant improvement in back pain for the new and the old drugs, and new minus old. Yeah, I think it's important to say new minus old there, just to show which way you're subtracting it, even though maybe it's a little bit obvious. So there you go. The difference in this one, once again, patients like these, if you haven't had random selection, SRS. Okay, great. Number two says the fact that 84 patients were not randomly selected leads to what form of conclusion? Well, that's what I've said like 2 or 3 times now. And so we're going to say it one more time. If they're not randomly selected, we can only infer about patients like these, that we have reason to believe are like these. And the random condition is met if they've been randomly assigned to treatment groups, which they were. So the random condition was met. All right. And so we can only infer or generalize about patients that we have reason to believe are like these 84 patients. So there we go. And then lastly, does the interval give us statistically significant evidence that the new drug works better than the old drug? In other words, is 0 in the interval, so to speak? You'll notice 0's in the interval. You got some negative values, some positive values. So there's plausibly no difference in the treatments. So we would say no. Make sure and answer the questions being asked. No. All right. 0 is inside the interval. So there's plausibly no difference in the true. There's no difference in the true. I didn't word that well. There's plausibly no difference in the proportions. Yeah, there's possibly no difference in the proportions of patients who would show improvement between the new and old drugs. So 0 represents no difference, and it is a plausible value. So, okay, that's it. That is two proportion Z intervals. I thank you for watching this video. If you have any questions, this can be, you know, maybe a little bit complicated, and you're gonna have to study this to be good at writing. You got to study this to become good at writing the little mini essay. And I encourage you to send me questions. Thanks for watching the video, and I hope you have a great day.